Hey, pre-calc. Well, after a really quick Unit 2 on complex fractions, we're ready to jump right into Unit 3 on functions. So if you open the new packet and turn to the very first page, these notes are included in your packet. And the very first thing we have to recall is how do we define a function? And you start doing work with functions back in Algebra 1, maybe not as much in geometry, but certainly build upon these ideas in Algebra 2. And of course, we'll build upon them even further in pre-calc. So you can see that at the top we have a list of things that are relations, but not all relations are functions. So we're going to look at some examples, and there's two columns to consider. We have a bunch of functions in the left column here, and then things that would just be considered relations, but not functions in the right column. So take a look at the first example where we have two sets of ordered pairs. And again, this one's a function, this one's not, and I want you to start recalling what makes something a function. In the graphical representation here, number 2 is an example of something that is a function, whereas this one on the right-hand side is not a function. And finally, number 3, when we deal with some cases of mapping where we take elements of one set and map them over to a different set, this would be a function, but this one would not. So what we're trying to build here is a definition for what a function is, and I know that that's what is asked of you right below this. So if you would take a minute, think about what your definition of a function is, go ahead and write that down and hit pause because I'm about to reveal my definition. So a function in my own words is a relation in which each input has a unique output. Right? So if we take a look at all the inputs for the ordered pairs and the sets up here, each input 1, 2, and 4 had a unique output. Whereas in relation B, the input of 2 did not have a unique output. It had two different outputs, 3 and 7. If you look at this graph, every x value has a unique y value, but here an x value of 5 has two different y values. And finally, in the mapping examples, here the input of A does not have a unique output. It maps to 1 and 2. Whereas even though in this mapping A and B both map to 1, that's okay because this input has just one output it corresponds with. When an input corresponds with more than one output, then we have an issue and it's not a function. So something you're probably familiar with as it relates to the graphs of functions is a certain test that we can use to determine whether or not something's a function. So right below this, it says the vertical line test can be used to determine whether or not a relation is in fact a function. So what do we mean by the vertical line test? Well, if you can draw a vertical line anywhere on the graph such that it only intersects and hits the graph once, then it passes the vertical line test. However, if you draw a vertical line and it hits the graph more than once, it breaks our definition of each input having a unique output. So if we take a look at this graph right here, and maybe this graph kind of looks familiar to you, it's a function that you would have studied last year. No matter where you draw a vertical line, it's only going to ever hit the graph once. It doesn't matter where you draw that vertical line. So if I were to ask you the question, is this a function in this first example, the answer would be yes. It passes the vertical line test. Moving on to something like the middle graph here, maybe even this looks familiar from something you would have studied in past years of algebra. Okay, if you're unsure, keep drawing those vertical lines. Yeah, there's definitely something weird happening at x equals 2, right? But it's not that it's an issue with failing the vertical line test. It doesn't hit the graph more than once. So I would say, yes, this is a function too. And then very clearly, once we get to the last example, it's a really nice looking heart, but darn, it's not a function. Clearly that vertical line hits in more than one place. So is this a function? No. Fails the vertical line test. Okay, so that's a pretty quick and easy test to say yes or no to functions. If you turn to the next page, page 2, at the very top, we're going to recall what domain and range are as they relate to functions. And very simply put, the domain is the set of inputs. So what we're allowed to plug in for x, and then the range would be a set containing the outputs for a given function. So we'll start with some things that, again, I think should be pretty familiar to us. We have f of x equals x squared, this parabola shape, and this is kind of a screenshot from a graphing calculator. So those arrows, if we were to sketch this by hand, would extend up forever there. And what I'll say when I write the domain and range is I'm going to use what's called interval notation, which I'm pretty sure among students and certainly among teachers, that is a preferred notation. It just looks the nicest. Interval notation uses maybe a series of parentheses and brackets to express the set of x values for the domain, and then the range would be the y values, right? So we have the x-axis here, we have the y-axis here. When I think about domain, I always scan the graph from left to right along the x-axis, and then looking at the graph, determine what x values is this graph defined for. Well, I'm hoping you see based on these arrows that this graph is going to go to the left forever, and it's also going to head up and to the right forever and ever and ever. So how do we express forever and ever in math language? Well, we would say that the domain is all real numbers, which in interval notation is negative infinity to infinity. You always, always, always will use parentheses around infinity. And then meanwhile, when I talk about the range, we're talking about the y values. So I scan the graph from the bottom to the top of the page because we're looking at the y-axis now. So starting at the bottom, I can see the graph isn't defined really for any negative y values. But the first y value that we hit right here is at 0. And then if I continue up, this graph will go up forever after that value. So make sure that you include 0 in the range with a bracket. Okay. An input of 0 would have an output of 0, so we can include that. But as a reminder, infinity will always get parentheses there. Okay, moving on to the second example here. F of x equals the square root of x plus 4. So in this example, we have a function that's a radical function. You can see kind of it has this unique starting point, and then if I were to draw an arrow, we'd have an arrow on this end of the graph. So we talk about domain and range. Thinking about domain, start on the left side and scan from left to right. Okay, the first place I have to stop is when x equals -4, right? That's the first x value that this function is defined for. And then from there, we go from -4 to the right forever. So we'll say that the domain is -4 to infinity. And meanwhile, the range, similar idea, right? Just go bottom to top. The first y value we hit is 0 again. And although it's a very slow rate of growth when we're talking about radical functions, this graph will very slowly go up and up and up and up forever and ever and ever. So the range, therefore, is 0 to infinity, right? Definitely doesn't grow as fast as a y equals x squared does, the parabola we just sketched, but this one will also go to infinity. So I think you're pretty familiar with what the notation for functions are. We have f of x and g of x defined down here, just as kind of a reminder of how do we evaluate functions. If I asked you to compute f of 2, what would that look like? You're simply going to replace all the x's in your function with that numerical value 2. So it'd be 2 times 2 squared plus 5 times 2 plus 1. And then here comes the hard part, just figuring out what all that is. Make sure you do PEMDAS if you don't have a calculator, right? Calculator knows PEMDAS for you, but 2 squared is 4, times that 2 is 8, plus 5 times 2 would be 10, plus 1, so it looks like this is a total of 19. Moving over to f of -3, same idea, right? 2 times -3 squared, plus 5 times -3 plus 1. Again, without a calculator, just be cautious here that when you do -3 squared, the parentheses around that -3 make that a +9, times 2 is 18, minus 15 in the middle, plus 1, so 3 plus 1 would be a total of 4. At this point, I really have nothing against you typing that into the calculator, but, it's up to you. I guess it would also depend on a test if you had a calculator available to you for something like that. We will certainly have some tests this year that are non-calculator tests. All right, moving over to the right side, similar example, we're going back to x squared as our function rule, but notice how the inputs are all going to look a little bit different. We're inputting variables now, okay? So to do g of a, it's the same idea. You're replacing x in your function with the quantity a. So this would be a squared. You don't really need the parentheses around that anymore, right? A to the second power is just a squared. When I do g of a plus 1, take that x out and replace it with the entire quantity, a plus 1. Do not make that classic student mistake of distributing the square into the parentheses. That's illegal mathematics. The math police are going to come and get you, all right? But if you were to multiply this by itself with box method or any other method, the trinomial you would get is a squared plus 2a plus 1. And then finally, the last example down there, g of a cubed, that would be a cubed squared. So a to the third to the second. The rule when you do a power to a power is you multiply those, right? You can also think of this as multiplying a cubed times itself. A cubed times a cubed is a to the sixth. So just a little bit of practice there that students do tend to have a tougher time when subbing an expression in, like a plus 1, to their function. So we'll see that come up in other contexts when we get into some of the other algebra related to functions, okay? We're going to go to the next page, page 3. And the last part of our Intro to Functions Day is about what I've called important functions. So for each of the examples, it says list the function family. So what do all functions of this form, what are they called? And then we're going to list the domain and range, and we'll sketch a graph. I think that the first 4 should be of a high level of comfort for you. You should probably know in a pre-calc class what the graph of f of x equals 2x minus 3 looks like, or y equals 2x minus 3. F of x equals 4, I mean, just think about it. Think about what that sketch looks like. Tell me what you think the name of the function is. Write the domain and range. I'll also let you think about x squared and x cubed. Okay, worst case scenario, type it into your calculator and see what it looks like. But I challenge yourself to, I think you can rack your brains from Algebra 2 last year and recall really what each of these look like. So that will bring me, I guess, over to page 4 then of the packet. And this is the page, I'll do this page with you because there are maybe some tougher functions that will come up on this page. So I want to make sure we talk about them and have some good context for you to go back to page 3 and fill in 1 through 4. So for number 5, I would give this the name of a radical function. You might in a textbook see this called a root function, right? We're taking a square root of x. So the radical function is going to have a sketch that looks like this, which maybe is not too surprising. Didn't we see a radical function sketched over here a second ago? But it was that same graph moved to the left for, oh yeah, and that kind of makes sense based on what was underneath the radical symbol. We'll talk about transformations more in this unit too. But we've got a radical function, the domain and range. Well, when I think about what I'm allowed to input for x, I can't input anything negative. So we're going to say 0 to infinity, which we can confirm graphically. Square root of a negative is a non-real result. And then the range would also be 0 to infinity. Okay. Taking a look at number 6, 1 over x. So the name of this graph, I'm going to write 2 different things here. This is sometimes known as the reciprocal function. Okay, y equals x is the identity function, and if you find the reciprocal of that, you get 1 over x. I also might call this a rational function. Rational functions are functions that are fractions with a variable in the denominator. We'll do a whole unit of study just about those. One of my favorites. All right, what do we think about rational functions? Well, I'll show you what the graph looks like here. It actually is similar to one of the graphs that we looked at when we were saying yes or no to functions at the beginning of the lesson. Here's what the graph looks like. If you pick some inputs and found the outputs, you get a graph that looks like this. So notice how we're getting really, really close to the y-axis, but never touching it, right? And the reason being is that I can't plug in 0 for x. 1 over 0 is undefined. So since 0 is not in the domain, the way we would write that is we have everything from negative infinity up to 0, but then stop, and then pick up on the other side, and we'll say from 0 to infinity. And this is a notation that you should be fairly familiar with. I know you do this a lot in Algebra 2 when writing domains and ranges. And very similarly, when I go from bottom to top, you notice we're never going to cross and touch the x-axis. And therefore, the range is negative infinity to 0, union 0 to infinity. So I might ask you in class when I see you next, what are the names? I don't think I've mentioned it yet. Of the lines that the graph never crosses. Right, so we have this vertical line on the y-axis, a horizontal line on the x-axis. The graph's never going to cross those lines. What are the names of those lines? So make sure you're ready for an answer with that next time. If you have to Google it, no big deal, but I want you to be able to tell me an answer if I ask you in class. All right, last two, f of x equals absolute value of x, and as I've read it, that's the name of the function, right? It's the absolute value family of functions. And in this absolute value family, if I think about the graph, you might recall that it looks like that V shape. So the domain is, well, it's going to go to the left forever. It's going to go to the right forever, all real numbers, negative infinity to infinity. The range, very similar to y equals x squared. It starts at 0, right? There's no negative outputs because the absolute value of a quantity is always positive. So we can include 0 and go to infinity. Okay. Finally, the last one, and this one might be one of the newer ones for you. I don't think you study this in Algebra 2, but these are square brackets around x. And when you have square brackets around x, I'll say that this is called the greatest integer function. If you took Algebra 2 honors last year, you would have studied this function. But what does the greatest integer function do? If you were to plug in a value for x, that's an integer, out pops an integer. So for example, the greatest integer of 2 is 2. The greatest integer of -1 is -1. But if you plug in something that's a non-integer, like let's pretend like we plug in 3.8, that's not an integer. The output is the greatest integer less than that number. So you're not going to round this up necessarily. In fact, it always rounds down to the integer right below it. Okay. So if I were to give you, the absolute value of -2.1, students always get messed up with this with negative integers because they write that the answer is -2. But what's the greatest integer less than this? It bumps down to -3. So what is this graph going to even look like then? If I can only graph things such that the outputted values are integers. Well, I'll tell you, when you plug in 0, you get 0, because 0 is an integer. And anything you plug in between 0 and 1, it's going to output 0. Right? If you plug in 0.5, knocks it down to 0. 0.7 knocks it down to 0. But as soon as I get to 1, I'm going to put an open circle there, because now when I plug in 1 for x, the output is 1. And everything between 1 and 2, like 1.1, 1.2, 1.3, all the way up through like 1.8, 1.9, it's going to output 1. But the second I plug in 2, now the output is a 2, and we get this very cool looking function, which actually has a lot of very practical real life applications that looks like this. And because the graph looks like this, it is very commonly referred to as the step function. Right? You can just like hop from one step to the next here. So I'll talk more about this function in other units later on, but we've got this thing called the greatest integer function, which looks like a series of steps. The domain of this function is actually all reals. You can plug in whatever you want for x. It's not as easy to write the range for us, but if you're thinking about the range and you just said it's all integers, that's fine. So the set of integers I'm going to write as this funny looking z. Okay, this symbol mathematically represents the set of all integers. So again, I realize this is probably a new looking graph for many of you, but we'll do more practice with this at some point. So let me know if you have any questions. Please make sure that by the next time I see you, you've also filled in page 3 where it started with these important functions. Okay, we're going to fly through that, talk a little bit more about function notation, domain and range, and then we'll go from there. All right, that's a quick first lesson on intro to functions here. Have a great